Number 6, part C, use Euler's method to estimate the output when the input is 2.4. Use two equal step sizes, which means since we know what x and y is when x is 2, to get to 2.4, we're going to use a step size of 0.2. Euler's method requires that we know the slope at each point before we go to the next point. So the slope when x is 2, g prime of 2, is 4. Which brings us to the formula for the next y value. It's when x is 2.2, we approximate that the next y value will be the previous y value plus the step size multiplied by the slope at the previous point. Alright, when x is 2.2, we predict the y value, g of x, will be about 3.8. What about the slope when x is 2.2? That's 7. Alright, next step. The y value is estimated to be the previous y value plus the step size times the slope at the previous y value, previous x value. I didn't write that down yet. When x is 2.2, the slope g prime of 2.2 is said to be 7. Alright, so that goes there, and this gives us our 5.2. So our estimate when x is 2.4 is that g will be about 5.2. Part D asks for the second degree Taylor polynomial centered at 2. Using the formula for the Taylor polynomial, a Taylor polynomial for function g, it'll be the 0th derivative at where it's centered, x minus where it's centered, to the 0 power of 0 factorial, plus the first derivative where it's centered, x minus where it's centered, to the first power over 1 factorial, plus the second derivative where it's centered, times x minus where it's centered, to the second power over 2 factorial. And that'll do it for the second degree Taylor polynomial centered at 2. Alright, g of 0 of 2 just means g of 2, which is 3. G prime of 2 is 4. And g double prime of 2 was given as 20. Therefore, our second degree Taylor polynomial centered at 2 is right there. And use this to approximate g of 2.4. 6.2. The actual value of g when we input 2.4 is approximately the output from the second degree Taylor polynomial, which is about 6.2. And then it says, show that this approximation is correct to within 1/10. To do this, we're going to use the Taylor remainder theorem, otherwise known as the Lagrange error bound theorem. The exact value is our approximate value plus the remainder, or the error. So the exact value minus our approximation is equal to the error, or our remainder, and we can bound that error by the first unused term of our Taylor formula with a small twist that instead of this value being c, it's going to be z. Z is some value between where it's centered 2 and where we're evaluating it 2.4. And that error bound is bound by the product of the maximum third derivative of some value z between 2.4 and 2 times this value to the third over 3 factorial. And this is just the Taylor formula for the third degree term, except for that we have a z here instead. Alright, so z has to be between 2 and 2.4, and this problem says that it will never exceed 6 on that interval. So on this interval, we know that the maximum value is 6. So our error bound is, so that's 6 times 0.4 to the third over 3 factorial, which is 6, which is just 0.4 to the third, which is 0.064, which is, as they asked us to prove, definitely less than 1/10. Problem done.